Hello, Honors Chemistry, and welcome to 13.9 and 13.10, the last two sections from Chapter 13, dealing with colligative properties, where colligative properties that we are talking about in this unit include freezing point depression, boiling point elevation, and osmotic pressure, right? Where all of these are things that depend not on the identity of the solute, but how much solute is present in a solution, right? The more solute that is present, the bigger the effect, okay? For freezing point depression and boiling point elevation, right? And so, like, the word means what it says, right? So as in it depresses the freezing point, lowers the freezing point, right? Elevates or increases the boiling point, right? So the presence of a solute does both of these things, right? And the simplest way to look at that is what we are doing is we are extending the range over which something is a liquid, okay? We are extending the range over which something is a liquid. So if we look at this, right, here, this is this little diagram that I stole from an online textbook, right, says that here is our normal boiling point for water, here's our normal freezing point for water, and this is the range over which that water would be a liquid normally, right? But by adding solute, what we can do is we can increase that range over which water behaves as a liquid, right? Which is useful for lots and lots of things. And at the particle level, we can think of this as the solute particles, right? Going back to the very beginning of chapter 13 when we talk about dissolving, right? The solute has an effect on the solvent, right? It rearranges how the solvent interacts, right? It changes how the solvent interacts with each other because now they're also interacting with the solute, right? And so by disrupting the way that, for in this case, right, water molecules interact with each other, right, we can basically get them to stay a liquid longer, okay? We'll get into more of those details in further units, right? But that's good for now. It does introduce the new concept of molality, which is a lowercase m, right? And it is moles of solute per kilogram of solvent, right? And it gives us our equations, which say that our freezing point depression is going to be equal to the molality of our solution. Again, molality of our solution times our Kf value, right? And our freezing point, our boiling point elevation, same thing, right? We would have our molality times our Kb, right? Now, these are for water, right? Because again, water is mostly what we are talking about, right? For water, and you'll see that the Kf is much bigger than the Kb, yes? Kf is much bigger than Kb, which means that as we add solute, we have a significant impact on the freezing point, right? More so than we do the boiling point, right? Like we can increase the boiling point, just not to the same extent as we do for the freezing point. All right, so let's go ahead and do some practice here, right? So first it says calculate the molality of a sucrose solution containing 50.4 grams of sucrose and that many kilograms of water, right? So again, we are going to do moles of solute over kilograms of solvent. So we would take our 50.4 grams of sucrose, so C12, H22, O11, right? And then we would have to turn that into moles. So we have 342.34 grams of sucrose for every 1 mole of sucrose. And then, so that would give us our mole part, right? And then we're going to take that whole thing, and so again, visually, however it makes sense to you, right? This whole thing is going to go over the kilograms of solvent, so 0.332 kilograms of water, right? And that's going to give us our molality, yes? Now, follow-up question says to calculate the freezing point of a 2.6 molal sucrose solution. So the change in freezing point is going to be equal to my molality, which is 2.6 molal, times our Kf for water, which is 1.86 degrees Celsius, times kilograms of solvent over moles of solute. Now, right, once we take these, right, and then if we write out these units neatly like we're supposed to, right, so this would be our moles, right, and this would be our kilograms of solvent, right, and so those would cancel, right, this would cancel, right, and 2.6 times 1.86 is going to give us our delta TF, right, and that would be the change in the freezing point, right, And we know that the freezing point is 0 degrees Celsius, right? So that is how much colder than 0 degrees Celsius our freezing point would be for this solution. Yes? Does that make sense? All right, and then boiling point would work the same way, where we just use that equation. Now, osmotic pressure is a weird concept, right? So the concept of there being a pressure that is applied is a little bit weird and hard to understand, right? But the concept of things being more concentrated or less concentrated, I think we should be able to understand that. And the movement of water, right? Which you talk about some in biology when you talk about cell membranes, right? Where water will have a tendency, so if we have a semi-permeable membrane, and there are lots of different types of semi-permeable membranes, right? But most often it allows water to pass through, right? And so then water will move, right? So that it's equalizing the concentration on both sides of that semi-permeable membrane, right? Here we have a picture of some intestines, right? And if we look, right, if we have a high salt concentration in the intestine, water will preferentially move into your intestines, right? So again, high salt content in the intestine means that water preferentially moves into the intestine, right? And typically water is moving out of the intestine, right? Because typically that's where we absorb water from, right? But anyway, water moves into the intestines, which leads to, ding, 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 right, diarrhea. Okay, now, on a different level, right, we can look at cells, right, and their semi-permeable membranes, right, where here we have a picture of normal blood cells in picture A, right, and red blood cells in pure water, right? So pure water have no ions and no solutes floating around, so then water preferentially moves from the water through the membrane into the cell in an effort to dilute what's in the cell such that everybody comes out at the same concentration, right? And by coming out at the same concentration, right, we reach that place that it's talking about in the osmotic pressure section where the pressures are equilibrated, right? Or we could have a situation where the red blood cell is in a concentrated solution, right? And when we say that we put the red blood cell in a concentrated solution, we simply mean that the outside environment has more solute in it, yes? Higher concentration of solute in it, which means that water will preferentially move out of the cell, right? And if water preferentially moves out of the cell, then now the concentration of water in the cell is too low, right? And the cells tend to shrivel up, right? And so that's really the extent to which there are equations and things you can do, but that's beyond the scope of what we're going to cover. All right. Thank you for listening. Be good, and I will see you soon for lots of practice. All right, bye.